During the 3 weeks it took to plan, design, and test the robot, I spent a large sum of each class documenting the day-by-day progress, as well as the struggles we encountered. I collected a large sum of pictures, video, high-speed footage, and time-lapses to capture every detail at every angle. From extensive photo evidence to corny transitional clips, the footage taken helped our group better our robot and this project. The robot design began with a simple prototype with only the light sensors attached. As we improved the code, we added the touch and distance sensors. These sensors were then rearranged and fine-tuned to peak performance. The final version of our robot had a centered touch sensor, so it would connect with the brick even if there were slight deviation in the travel path. Additionally, the color sensors were placed parallel to the wheels and lowered slightly to establish more accurate color detection. But the robot isn't the only thing we had to re-engineer. The code itself went through many revisions and additions before the final product. Our first attempts were to calculate and display the threshold values collected by the sensors. Only after we accomplished that did we even attempt to make it move. Once we got it moving, we tested the robot going at different speeds to see how fast we could get it to go and still follow the line. We also experimented with different types of turns to best accommodate the sharper turns. The optimization of our code proved to be just as important as our physical design. The most interesting but frustrating part of my job was documenting the struggles we had. Most of the early obstacles were small, tedious mistakes in our code, but the real trouble came during the distance sensor phase. For reasons still unknown, the robot would not perform the desired maneuvers when the distance sensor was triggered. After many days of troubleshooting and testing, we concluded that the problem was internal and out of our control. Much of my frustration was spent to figure this out. But overall, the project was a fun one to document. The abilities I had access to for video recording gave me fun and efficient ways to gather information on our robot and our team, from assigning to completion.
It was quite difficult to figure out where to start in our code. Primarily, we weren't sure because we did not have a well-thought-out pseudocode to guide us. Coding would have gone much smoother if we did. Also, we realized after the test day that our code did not include many comments. Adding more comments to our code could have also given us help when deciding what worked and what didn't. There were times when we didn't know what our code was doing at a specific line because of the lack of comments. We first decided to calibrate the threshold. We did this by getting the white reflected color value and the black reflected color value and adding these values and dividing it by 2 to get our threshold value. The first problem that we encountered with our code was figuring out what type of loop to use. We weren't completely sure what type of loop to use to execute our first task, which is to follow the line. Also, because the project required us to create nested loops, it was easy to get confused when figuring out which brackets go with which loop. Another problem that we encountered was the lack of time management. There were days when we would spend the entire class trying to code a specific task that seemed so simple to code but took us longer than expected. Because we didn't pace ourselves very well, we didn't have enough time to work on the other portions of the robot. To fix these problems, we could have skipped one task that seemed more difficult than the others and code another task that seemed easier to execute. By doing this, we don't waste time trying to figure out what went wrong and instead use our time to finish coding the other aspects of the robot. In the end, our robot did not give us the results that we had hoped for. The lack of comments, spending too much time on one specific task, and not having the resources such as a well-thought-out pseudocode kept us from achieving our goal. These problems should have been fixed in order to achieve success.
Our initial brainstorm consisted of robot design, course trajectory, code development, and distribution of tasks. The first few days after the introduction of the Line Follower Challenge caught our group in a fruitful mindset with several formative ideas that would ultimately influence our final and lasting design. The first step we took in our endeavor was to design a robot that could properly correspond and interact with the line follower course. Secondly, we shifted focus towards code development. This step took several different approaches in terms of who would specialize with which section of code. Thirdly, we had to anticipate the course outline so that we could properly design the robot. Finally, the last part of our brainstorm was who would complete which tasks. Our imagination for the ideal robot design grew out of a model that member Joey Connolly developed prior to the first day of hands-on work for the challenge. His robot featured 4 main sensors and pivoting wheels built on separate axles to mobilize turning abilities. Although the robot exceeded the height limit, it did give us the necessary means to the development of our resulting robot. With Connolly's robot as our model, we downgrade the size of the body, but enhance the settings for each sensor. After much consideration, the robot was altered to a version that would fit the requirements and hopefully exceed expectations. The next step consisted of our conceptualizing of the code that would program the robot. Initially, all the members were devoted to a section of code. We envisioned that the code, although lengthy, would prove to successfully traverse the line follower chord. Next, picturing how the robot would relate to the trajectory of the course could only be thought of with an initial idea of the code that would accompany the robot across the course. However, understanding the obstacles of the course would prove to be an important factor in the imagination process of the early development for the challenge. The final step for the brainstorm is defined by the distribution of tasks to each member of the group. Prior to the distribution, each member had a shared responsibility for each aspect of the early development of our robot. Moreover, as time passed, we decided on specific tasks to perform. The initial tasks were coding, building, documenting, and perfecting. Initially, Sal focused on the coding and Joey focused on building, while Nick, Jack, and Nico centered on building, perfecting, and documenting. In terms of building, Joey created the prototype robot, and Nick, Jack, and Nico took from Joey's example to build the final version of the robot. Those who worked on perfecting the body of the robot dealt with any possible sources of error in the early stages of development.
How do you feel about that?